Alright, hey guys, it's Miss Summers with your Unit 2 recap video. This video is going to cover all topics that we talked about from our second unit, which is astronomy. We're going to go in order from the first topic that we talked about all the way to the last. So let's get started with laws and theories. Alright, so for this unit and a lot of our units, we're going to be talking about scientific theories and scientific laws and what their differences are. Alright. Theories, unfortunately, don't get a good rap. Alright, you'll hear people be like, well, that's just a theory. Kind of like, oh, that doesn't really mean anything, or it doesn't really, we don't really know. But that's not what a theory means in science. In science, a theory is something that explains a natural phenomenon, alright? And not only does it explain it, it's well supported by multiple pieces of evidence over multiple observations. So we can use theories to predict what's going to happen in the future. Alright, that's different than a law. Laws are also helpful. They don't explain things though. Laws describe phenomenon, alright? So they're going to tell us, hey, this happens. Hey, that's going to happen. Hey, this will happen. It's going to happen like that. All right, but it's not telling me why it does that. So one way you can remember theories end in a Y because they are explaining why does it happen. Laws end in a W, what is happening. Okay, so let's start with our first two theories that we talked about in astronomy. Our first two theories are Big Bang theory, and I'll make a little T-chart here, and nebular theory. All right. So these are two theories that both explain something about the formation of our universe, space, wherever we are. All right, so let's start with the Big Bang. That's probably one you're somewhat familiar with. All right, so the Big Bang theory states that the universe started as a singular point or a singularity. So a little dot like that. Okay, where the singularity came from, what made this singularity? That's a good question. That's something that scientists are still working on, which is okay. Science is a process. All right. According to Big Bang theory, this singularity started expanding about 14 billion years ago. All right, something happened and it started to expand. It was infinitely dense at the beginning. It was super packed. But it took up a very, very small space. And it started to expand. And as it expands, it cooled down. And because it cooled down, things like matter can condense. So things like protons and neutrons and stuff like that. And that's how you got matter and stuff. All right? Now, that might be like, oh, okay, that's really cool. How do we know that? Because remember, theories are supported by evidence. The main piece of evidence I want you to know for Big Bang theory is something called redshift. Redshift is redshift is a byproduct of the Doppler effect, all right? So if you've ever been in a car and an ambulance is coming your way, okay, coming from the other way, you pull over to the side, you stop like you should. As that ambulance gets closer, you may notice the noise changes. So not only does it obviously get louder because it's closer, but the noise itself will get a more higher pitched. That's because as that ambulance moves towards you, the sound waves that it's producing are getting squished together. All right, and that results in a higher pitch. And likewise, once the ambulance passes you, is moving away, those sound waves stretch out because the source of the sound, the source of the waves is moving. All right, so obviously we don't hear the universe, we see light, and that is what we're observing with redshift. As we look at faraway galaxies. Okay, here we are. That's us, everybody. And here's a galaxy far, far away. This is just your typical spiral galaxy. All right. We can tell the light that's being emitted from that galaxy. So here's the light. Okay, light travels in waves that kind of look like this for all intents and purposes. Those waves are getting stretched out. All right, so by the time they reach us, they are stretchier. All right, and that's how we know that things are moving apart. So we use our power of deduction and inference. Well, if things are moving apart, that means they used to be closer together. And that's how we come about to this idea that everything started as this singularity. Now, there's a couple other pieces of evidence like cosmic background radiation and the percentage of certain elements in the universe, but this is the one that I want you to know for ninth grade earth science, okay? Our other theory is nebular theory. So Big Bang has to do with the universe. Nebular theory has to do with stars, solar systems, and planets. All right, how do we get all this other fun little stuff that we live on? All right, so what nebular theory states is that all stars, planets, galaxies, solar systems, they all start as these big old blobs of hydrogen gas and dust and like little trace elements here and there. All right, all swirly whirling around. Okay, this is called a nebula. A nebula. Okay, and according to nebular theory, something happens to this nebula. Okay, some force acts upon this nebula. So maybe it's like a blast of radiation from like a black hole or a supernova or something like that. And this big old cloud of gas and dust starts to rotate. And as it rotates, I'm going to scoot myself just over here a little so you can see this next picture. As it starts to rotate, this nebula starts to flatten. And your matter, so like your hydrogen gas and whatnot, all condenses to the middle by the powers of gravity. All right, gravity makes things coalesce in the center. All right. In this case, let's say this is the start of a solar system, okay? Here in the middle, we would have all this hydrogen smushed together. There'd be so much pressure, it would get really hot. You could start a process called fusion, and that, when fusion happens, that's when you get a star, all right? And then you have these little chunks of other matter that would become planets going around it, all right? So that would be how our solar system got here. Now, what are the evidences of nebular theory? Because remember, all theories have evidence to support them. All theories have evidence to support them. All right. There's a couple of different evidences. Number one, we can see this process. We literally can see nebula, and we can see little baby stars being born. You might be saying, how do you know it's a baby star? It's how much hydrogen there is. How do you know how much hydrogen there is? You ask it? No. You look at the light that's coming off of it. We can see that in solar systems, our solar system especially, all planets orbit on the same kind of elliptical plane. They all are sort of on this disk, if you will. You know, they go at different speeds, obviously, which we'll get to in a minute. But it's not like you have one planet going this way and another one going that way and another one going like, you know, making a figure eight. All right, they're all rotating the same way, or revolving the same way, excuse me. And all planets do rotate the same way, in our solar system at least. The only exception is Venus. Now, why is that an exception? I like to tell this story. The hypothesis, remember, our hypothesis is a proposed answer to something. The hypothesis why Venus spins backwards and not forward like the rest of the planets is because somewhere along Venus's history, the planet of Venus must have been struck by an enormous object, maybe like another planet or like a big old asteroid, something like that, and it caused it to start spinning the other way. Whoop. All right, that's nebular theory. All right, those are our two theories, our two explanations on how the universe got here and how we ended up with stars, solar systems, and planets. All right, so now that we have that, now we can focus more on planets, all right? So instead of a theory, we're now going to talk about some laws. The laws we're going to talk about are Keplers Laws. Ooh, Kepler, our boy Johannes Kepler. Most underrated astronomer in my opinion. Among astronomers, he's not super underrated, but like just in general science, like nobody's ever like, oh, Johannes Kepler, he's my favorite scientist. All right, so our friend Kepler came up with 3 laws about planetary motion. He came up with 3 laws. He observed, so he lived back in the 17th century, question mark. I'd have to check. But he was looking at data from the known planets, which would be at the time Mercury, Venus, Mars, Jupiter, and Saturn. The other planets had not been discovered yet by people. All right. And he came up with these 3 laws, these 3 descriptions, and he's like, all planets do this. All planets do this. Okay? The first law has to deal with the shape of the orbit. All right? He says that all planets go in ellipses. So planets don't go around the sun in a perfect circle. They make an oval shape. All right? So here's my oval. This is a very exaggerated oval. But you would have the sun at one focus of the oval or ellipse and nothing here. Now, the big thing with this law, the big aha moment, according to this model, if we go in an ellipse, that means sometimes we're closer to the sun and sometimes we're farther from the sun. All right? When we are closest to the sun, that is a place called perihelion. On Earth, perihelion generally happens in the first week of January. Keep that in mind. And when we are farthest from the sun, we are at aphelion. You can remember A is away. A is away. Aphelion generally happens around the first week of July. Keep that in mind. Okay? Now, with ellipses, we can describe different ellipses, different characteristics of ellipses, by talking about their eccentricity. All I need you to know about eccentricity, friends, eccentricity is how stretchy the oval is. So something like a circle has a very low eccentricity. This is not stretched out at all. It's a perfect circle. It's even on both sides. However, something like this, all right, this would be a very high eccentricity orbit. It's very stretched out, okay? I do not need you to know the mathematical formula for how to calculate eccentricities. If you know that, that's really neat. Good for you. I just need you to be able to compare. If I give you 2 orbits, you can say, all right, this one is more eccentric. It gets really, really close, then it gets really, really far away. Or this one has a very low eccentricity. There's not a big difference between perihelion and aphelion. Okay? Just for measure, or just to note, Earth has a relatively low eccentricity. Our eccentricity is like 0.00017, something very, very tiny. Our aphelion and our perihelion are only like 4 million miles apart. And you might be saying, wow, 4 million miles, that's a lot of miles. In the grand scheme of like space, it's not really. Okay? Our second law has to do with the speed of a planet's orbit. This is my favorite law. I love this law. All right? It is called the law of equal areas. All right? And before I jump into explaining it, let's do a little test. I have 2 containers here filled with liquid. I put some iodine in it. You know what? Let me put a little bit more here. Perfect. So I have 2 containers. They're just filled with water with some iodine in it so you can see. And I'm going to ask you, which one has the most liquid? And you, being very smart children, okay, if you ask like a 2-year-old this, they'll be like, the tall one has more. It's just because that's how their brains are. Bless their hearts. All right. You would be like Miss Summers. They both have the same amount because this one says 100 and it's filled up to the 100 mark, and so does this one. All right. And I would say, yes, they do have the same. Very good. All right. Even though they're different shapes, this is a taller container, but it's skinnier. This is a shorter container, but it's wider. All right. So if I apply that here, I'm going to draw my ellipse. There's my ellipse, Here's my sun. All right, here are my areas. This short wide triangle has the same area as this long skinny triangle. Do I need you to calculate it? No, I just need you to know if I give you this diagram, these are the same, even though they don't look the same. All right, when you are at perihelion, so remember, perihelion is when we're closer. the planet has to sweep out in this short, wide triangle. And when you're at aphelion, remember A is away, you sweep out in a tall, skinny triangle. Now, what that means, all right, keep in mind, I didn't tell you all of Kepler's second law. Kepler's second law, like the whole thing, says planets sweep out in equal areas in equal time intervals, all right? Well, the formula for the speed of something is equivalent to the distance over the time. Okay, speed is distance over time. So this triangle is made in the same amount of time that this triangle is. This planet at aphelion, or excuse me, perihelion, when it's closer at perihelion, it has to go a greater distance, all right? That's the bottom of this triangle compared to here. That means, and here's like the big aha moment, when you are at perihelion, when you are closer to the sun, you go faster. You go zippity zap zap zap. When you are at aphelion, that means, whoops, the opposite happens. You go slower. Now, the fun thing about this, remember, this is a law. Does our friend Kepler know exactly why this happens? Does he understand the mechanics of, okay, because the sun is this close, X, Y, and Z is going to happen, that's why the speed goes up? No, he doesn't know that yet. Okay? This doesn't explain why it happens. It just says it's going to happen, and it does. Now, the nifty thing about Kepler's laws, they don't just apply to planets. They apply to anything moving around another thing, so any orbiting body. All right? So the example I talk about in class, which is my favorite use of Kepler's second law, is the Apollo space mission, Apollo 13. All right? If you've ever seen the movie with Tom Hanks, pretty solid movie. You should totally check it out. All right, background story. You have 3 astronauts. They're supposed to go to the moon, get some pictures, collect some data, you know, hit a couple golf balls, go home. Yay. All right, halfway to the moon, there's an explosion on board. All right, they all have to evacuate to this lunar module. This lunar module wasn't made for 3 people. It only has so much air. It only has so much power. All right, so they call back home and they're like, Houston, we have a problem. That's where that comes from. All right, so the brains at NASA are like, well, how do we get these guys back home? All right, failure is not an option. So they're like, well, here's the Earth, here's the moon, and here's where y'all are at. And they're like, you can't just turn around in space. You can't just, because there's nothing to turn around. Like, there's just no way, okay? So they're like, you know what? We're going to use this. We need to give you a little power boost. How are we going to get you to do that? They were like, you're going to get as close to the moon as you can without landing on it. All right? And because they got super close to the moon, that increased their speed. So they were able to slingshot back to Earth. And they all survived. It was kind of a cool story. Really cool story. Check it out. All right? Pretty cool story. All right? Our third law has to deal with the time. All right, so this law has like a mathematical formula that goes with it. Let me show you what it is real quick, just for funsies. I gotta make sure this is right. It is, yes. Okay, so this 1 squared over that 2 squared is equal to R1 cubed over R2 cubed. You might be saying, Miss, how much, what's that mean? All right, T equals time of revolution. That's how long it takes for you to go around the planet. R is your average distance from the sun. Remember, it's average because sometimes we're closer and sometimes we're farther away. All right. Basically, if you take 2 planets and you compare this ratio, T1 squared, all right, the time of your revolution squared is equal to your average distance cubed. All right. What that basically means. I'm never going to ask you to do these problems unless you really want to. All right? If I have planets, the ones that are really close have really short years. Mercury goes around the sun in 88 days. All right, that's why it's called Mercury. It moves so quickly because it's really close. It doesn't have that far to go. Venus has a year of like 267 days. I could be making that up, I'm not going to lie. 200 some odd days. Earth is a little farther. Its year is a little longer, 365 Earth days. Mars, something like 600-ish Earth days. All right? The closer your planet is to the sun, the shorter your year is. And that kind of makes sense. It kind of makes sense. Like if we think about it like a racetrack, all right, if you ever watch like the long distance races at the Olympics or whatever, like the 800, the 4,000, you know, your 5Ks, your 10Ks, whatever, that are run on a track. Once everybody gets lined up and they tell them to go, everybody gets to as close to the middle as they can. Because it's a shorter distance. It doesn't take you as long to go, to get around. All right? So those are Kepler's 3 laws. All right? Kepler's 3 laws apply to all planets, moons going around planets, satellites going around planets, comets going around the sun, any orbiting body going around something else. All right? So that is our friend Kepler. All right? Those are his 3 laws. So now we've talked about, we talked about how the universe got here. We talked about how stars got here, and planets, and all that mess. Now let's talk about Earth, home sweet home, all right? The movements of Earth, all right? There are 5 vocab terms that you need to know about movement. The first one being barycenter. Barycenter is kind of like a seesaw. The barycenter is the point that two bodies orbit around. All right? So think of it like a seesaw. All right? If you have a seesaw, but your 2 people on the seesaw aren't the same size, the bigger person has to be closer to the center to balance it out. So I got an example here. All right? Here's my planet, the smaller mass, and here's my sun, the bigger mass. My barycenter is not going to be in the middle because that's not balanced. My barycenter is going to be more over here. There we go. Closer to the larger mass. Now, as it orbits, this larger mass also orbits this barycenter, okay? Which means what we can deduce from that, the sun moves a little bit. The sun is pulled off center a little bit by all these planets, all right? Each planet has its own barycenter with the sun. All right, so the sun's getting pulled in all different directions. All right, that's actually how we find other planets around other stars. Fun stuff. All right, always closer to the bigger mass. Our main motions, and these first 2 you probably have already heard about from like middle school or wherever, all right, is rotation or revolution. All right, rotation is just what it sounds like. We are spinning on the axis. Now, what you need to know is what that causes. That causes day and night, all right? Rotation causes day and night, all right? That's how we get this phenomenon. It only takes about 24 hours. So if you have a globe at home, I got this globe at the Goodwill. I love this globe. It's my favorite thing I've ever gotten from Goodwill. All right? It demonstrates rotation really nicely, all right? Now, let's say, let me turn it this way, okay? So this, there we go. Now it's tilted a little bit, all right? So let's pretend my face is the sun, all right? I can see all of North America. I can see most of South America. I can see most of the Atlantic Ocean, some of the Pacific Ocean, but I can't see like Asia and most of Africa. I can't see that here. That's because I am the daytime side, so all these folks are experiencing daytime. This is a shadow over here. All right, they're not seeing any light from me. All right, they're able to see stars and the moon and all that stuff. As it rotates, okay, North America, so there's North America coming towards you, so there's going through sunset now. Actually, I'm going the wrong way, LOL. Now I can see most of Asia. I'm starting to see parts of Eastern Africa and Europe. All right, but I can't see North America. All right, North America's at nighttime. That's rotation. Whee! All right, more proof that we live on a sphere. Whee! The other motion, revolution, is Earth going around that barycenter that we talked about. Now, because the sun is so much bigger than Earth, the barycenter is, for all intents and purposes, the sun. All right, so it's not like we're on like the sun is just moving a little bit, and we are like going in this ellipse around them. All right. One revolution takes 365.25 Earth days or Earth rotations. That's why we have to add in an extra day every 4 years. Is that 0.25? All right. But other than that, we're golden. All right. Revolution also has to do with seasons. We'll talk about seasons here in just a minute. Cool. Those are your two main motions. The other two motions are minor motions. They don't have as big of an impact on like day-to-day life, but they are important to know nonetheless. Our first one is precession. Precession is a very slow motion. It takes 26,000 years for one precessional cycle, all right? All right, watch. Here's precession, all right? Pretend, all right, over here where I'm pointing, that's where the North Star is. That's Polaris. Polaris, all right? So Earth is facing this way in space, and it's like orbiting around the sun, and it's rotating, and everyone's having a great day, okay? Through precession, here's what happens. Ready? Whee! Whee! And I'm over here now, all right? Now, the North Star is over here. This North Star is called Vega. Okay, that's where it's going to be in about 13,000 years, when it's about halfway through the cycle. And then another 13,000 years from now, whee! Now it's pointing towards y'all. Now y'all are the North Star. Now it's back where it started. Okay, this doesn't change the tilt of Earth. It changes where we face in space. It changes the orientation of our axis. Just which way are we facing? Which way are we facing? All right. That is in contrast to nutation. My favorite word that goes with nutation is a wobble. It's the wibble wobble. It's a wibble wobble that happens during precession. So here's precession. Here's nutation. Nutation is this wobbling of the axis. This changes the tilt of Earth ever so slightly. Ever so slightly. All right, so it's a very minor change. One nutation cycle takes about 18 years. So it is something that we will experience within our lifetimes. Because it changes the tilt, it's going to have mild effects on seasons. And we'll talk about that here right now. Let's talk about seasons, shall we? So, seasons got something to do with tilt, right? Let's draw some pictures. Let's draw a picture, shall we? Let's draw a picture. All right. So here's our sun. Not to scale, by the way. Remember, we go in an ellipse. All right, so there's my ellipse. I'm just a smidge closer on this side. I'm a smidge further on that side. So you might be thinking, well, closer or further? Does that mean it's winter time over here, where I'm further away? Because that would make sense, because in winter it's cold. And if you're not near the sun, it must be cold, right? Right? No, absolutely not. All right, seasons happen because the Earth is tilted at 23.5 degrees. And we're going to talk about why we know that number. Okay, when we are at perihelion in January, technically perihelion, like, seasons happen over here. All right, but when we are closer to the sun, all right, the Earth actually looks like this. Okay? And when we are farther from the sun, closer to aphelion, we look like this. Change that a little bit. I had that tilt slightly exaggerated so you can see it a little better. Okay? So, how do I know it's tilted at 23.5 degrees? All right? Whenever a hemisphere of Earth, remember, a hemisphere is a half of Earth. Okay, we live in the northern hemisphere, so generally that's the one we're concerned about, because that's us. Okay, when we are facing away when we are tilted away from the sun, that means it is winter, okay? It's winter because the sun rays are still striking the surface, but they are more spread out. They are not concentrated, all right? Likewise, over here, when we are tilted towards the sun, we call that summer, all right? So the same sun rays, okay, these sun rays are spread out over this large area. These same sun rays are now concentrated, all right, which means it's going to be a little warmer. That's where you get those warmer temperatures from, all right? Now, how do I know the Earth is tilted at 23.5 degrees? Okay, how do we know that magical number, and how do I know when the Earth's tilt changes ever so slightly? On the first day of summer, that's called the summer equinox, the sun is directly over this latitude. Okay, in the north it's called the Tropic of Cancer. Let me make sure that's right real quick. Yes, haha, the Tropic of Cancer. All right. The Tropic of Cancer is 23.5 degrees above the equator. Okay. Likewise, if I go over here, note something. When the northern hemisphere, this is the north, when the northern hemisphere is tilted away, what do you notice about the southern hemisphere? The southern hemisphere is tilted towards. All right. In December, when we start winter, our friends in the southern hemisphere are experiencing summer. The sun is directly over the Tropic of Capricorn, which is also 23.5 degrees below the equator. So that's how we know this magical 23.5 number. That's where we got. We didn't just pull this out of our noggins. We weren't like, just like, here's that's like a good number. No, we had a reason. All right. So seasons happen not because of our distance from the sun, but because of the tilt. Okay. Now, let's talk about what would happen if we change the tilt. Okay. What happens if something changed with the tilt? Okay. Because nutation changes the tilt. All right. If we were to increase this tilt, okay, so let's say we increase this tilt from 23 degrees to 30 degrees. So the sun were, or excuse me, not the sun, the Earth were a little more on its side. You would end up with more extreme variations in temperature and seasonal changes, all right? The length of the day, and temperature is really what marks seasons. All right, more tilt, more extreme temperature variations, or more extreme variations in seasons. If there were no tilt, okay, let's see if we can figure it out. Well, if more tilt is more changes in seasons, no tilt would result in no seasons. Things would not change. You would not get this changing of how much sunlight you get throughout the year. Everything would stay the same all the time. All right. The other two words that I would like you to be familiar with for seasons are words that we associate with the beginnings of seasons. Okay. Our first word is solstice. All right. And I'm going to put solstice over here. And I'm going to put a solstice over here. Oh, you can't hardly but see that, can you? Solstice. All right. So what does solstice mean? Solstices are your first day of winter and summer. They are your longest or shortest day of the year. And it depends on where you are, whether it's the winter or the summer solstice. So here we are. All right, we're just coming out of winter when y'all are watching this video probably. Okay, we were experiencing winter solstice in December, but our friends in Australia were experiencing summer solstice. So I like to just call that the December solstice. Whereas in June, okay, as we approach the month of June, we will experience summer solstice in June, the longest day of the year, but our friends in the south will experience the winter solstice. So I just call it the June solstice, all right? The other terms that you need to know are equinox. So equinox is up here. Equinox is down here. They're 6 months apart. So equinox, you can kind of tell what it sounds like based on the word equa or equi. Kind of sounds like equal. All right. And nox, if you think about like the Romance languages, even German, which is not strictly a Romance language, has some Latin influence. All right. The word for nights, noches, Nacht. I don't know what it is in French, but I assume it's something similar. Comment below if you know how to say night in French. All right, or Portuguese. That would work too. All right, equinox means equal night. All right, these are the beginnings of spring and fall. And again, whether it's spring or fall depends on which hemisphere you're in. All right, on equinoxes, everybody gets 12 hours of daylight, 12 hours of sunshine. All right, same here, same there. 12 hours, all right? The sun's rays are directly over the equator. Everybody is getting sunshine, all right? So here, if I look at this diagram, well, here's winter in the north. Well, what season comes after winter? Well, spring, midsummers, of course. Very good. What's the opposite of spring? Fall. Opposite seasons happen in opposite hemispheres. Whatever it is in the northern hemisphere, the opposite is happening in the south because we live on a spheroid. We live on a spheroid. That's how we know. All right, if it's summer up here, it's winter down here. Okay, well, what comes after summer? Well, fall comes after summer, midsummers. It does, very good. What's the opposite of fall? Well, spring, midsummers. Very good. All you've got to be able to do with these diagrams, pals, you need to be able to identify where spring and summer are. Or excuse, you need to know where summer and winter are. All right? Summer and winter are always going to be on the sides. Okay? Now, sometimes your little Earth might be flipped the other way, so be mindful of that. Don't just memorize, oh, summer's always on the left-hand side or the right-hand side or whatever. No, it's not always like that. Okay? It'll always be on those sides, though. Okay? Yay! So that's seasons. All right? So seasons are a byproduct of the tilt of the Earth as well as the revolution. So let's talk about our next topic. All right, we've got 2 more topics to cover. And that will recap all of astronomy. Fantastic. All right? So the Earth's movement about the sun produces seasons. Now let's talk about the other body of the sky, the moon. The moon. All right? What does the moon do? What does the moon do for us? Ask not what the moon does for us, but what we can do for the moon. All right? The moon, what I want you to know, the moon is responsible for the tides of Earth. It is also responsible for nutation. That was part of why nutation happens. I'm not really sure about that, though. The moon is responsible for tides. All right? Gravity pulls water on Earth towards one side or the other, and that results in changing water levels. So sometimes the water level increases, sometimes it decreases, and we call that high and low tide. So wherever the moon is going to change how varied the tides are, or how extreme they are. All right, so let's start with the spring tide. Now, spring tide has nothing to do with the season. Okay, it's not called spring tide because it only happens in spring. That's not right. Spring tides happen because the Earth, here's the Earth, the moon, and the sun, put the sun over here, this big boy, are all in a line. Now, it doesn't matter if the sun's on this side or the sun's on that side. If they're in a straight line, they are a spring tide. Now, you might be saying, whoa, what's the sun doing here? The sun also creates gravity. All objects with mass have gravitational force, all right? Now, you might be saying, well, the sun's bigger, so does that mean it has a bigger effect? No. The moon has a bigger effect because it's closer, because it's super close. We're super tight with the moon, okay? During a spring tide, the moon and the sun act like they're on the same tug-of-war team. So they will pull more water towards the high tide side. All right? You get 2 pockets of water Okay, one on the side facing the moon and one on the direct opposite side because of inertia. These are your high tides. The other sides are your low tides. That's why you typically have 2 a day in most locations. All right, during a spring tide, you get higher highs and lower lows. All right, it is more extreme. You have a greater range, okay, a larger range. Just like in mathematics, a range, you subtract the biggest from the smallest, smallest from biggest thing. Potato, potato. All right, that's what we mean. All right, during a neap tide, neap tides happen when the Earth, here's the Earth, the moon, here's the moon, and the sun are at a 90-degree angle. So you're going to remember neap is 90. All right, neap is 90. Now the moon is still having the bigger influence because it's closest, so the high tide is still facing the moon, but the sun is pulling some of that water back to the low tide side. All right, so it's more evenly distributed. So during a neap tide, you're going to have lower high tides and higher low tides. We call that a smaller range. All right, it's not as different. So we can easily predict when spring tides and neap tides are going to happen by looking at the phase of the moon. When the moon is in a straight line with the sun and the earth, that is either a full moon, so it's like we can see the full face of the moon, or a new moon. A new moon is when it's completely in shadow. We can't see the face of it because Earth is in the way. All right. During a neap tide is going to happen during a quarter moon. All right. Now, what we call a quarter moon, you might colloquially call a half moon because it's half filled in. It's called a quarter because it's a quarter of the way through the lunar cycle. All right. So you see a moon looking like this, you're going to have really wimpy little tides. Lower highs, higher lows. When you see a full or new, that's when you get those great big spring tides. All right, you're going to have super great big high tides, super little low tides. All right, very important when you're studying marine biology. A lot of animals, especially ones that live in these tidal inlets, all right, the tides affect, when they're able to reproduce. Like if the tides aren't high enough, they're not going to be able to lay their little eggs, and their eggs aren't able to get out to sea or whatever, all right? So that's why we look at this. If you go surfing, surfers pay attention to tides a lot, all right? It's going to affect the size of the swells, your water levels. Surfers will pay attention to that. All sorts of reasons you would want to know about what the moon is, all right? Then our final topic in this massive recap of Unit 2 is the sun, the crown jewel of the solar system, the good old sun. All right, your main goal is to know why the sun makes life on Earth possible. So we're going to start with the sun itself, how it makes energy, how the energy gets to us, so on and so forth. So if we look at the sun, all right, first off, the sun is a star, okay? If you look at it like compared to other stars, it's not like a super great big star, but that's okay. It's a great star for us. Within the sun, you have a process called fusion. During fusion, 2 baby hydrogens are smushed together, and they are pushed together even though they don't want to be, and they fuse into a helium. All right? Now, during this process, all right, the mass of these 2 hydrogens does not equal the mass of this helium. All right, a little bit of that mass is lost. And you're like, wait a minute, I didn't think you could do that. I didn't think mass could go away like that. You're right, it can't. Some of that mass becomes energy, all right? And that energy is where it all starts, okay? We love that energy, all right? So again, this process is called fusion, all right? Now, this energy is in the form of light, all right? It's in the form of light. Light can be either visible light, which is like what we see, like colors, like RGB. It can also be heat, which is infrared. That's a longer wavelength. Or it can be ultraviolet, which is above blue, or above violet, which is the really super short wavelengths. That's like the not great kind. We don't love that kind. All right. So some of this energy from the sun, all right, is emitted out from the star, and it is going to make its merry way down to Earth. Okay? The method of heat transfer is radiation. All right, in this class, we're going to talk about radiation and convection mainly. Radiation is energy, the transfer of energy through electromagnetic waves, okay? This does not require like a medium, so it can go through space, which is why we love it. Because there's a lot of space between us and the sun. All right? That energy, which was created by the process of fusion, is going to radiate to Earth. All right? Our atmosphere is going to absorb some of that energy. Okay, like the ozone absorbs that bad UV radiation. We love that. Some of it's going to get reflected back. Some of it's going to bounce back and just go out its merry way into space. That's cool. Good for it. But most importantly, some of that heat is going to make it to the surface. And the surface is going to heat up. And that's a big deal. All right? When the surface is heated, that's what heats up the air above us. This process, all right, this energy keeps Earth warm enough where there can be liquid water. And that's the biggest thing we need for life. You have to have, from what we know, you have to have liquid water on the surface if you want to have life. All right? So let's talk about water. Let's talk about that for a second. Let's say I have two places on Earth, okay? Let's say I have two cities. All right, here's my two cities. And here's some water. Okay? Energy from the sun is going to heat up both of these places, but they're not going to heat them up equally. Okay, we have something called the differential heating of water and land. Okay, what I need you to know for right now, water takes a really long time to heat up and a really long time to cool down, because water has what's called a high specific heat capacity. I don't need you to know what that means. Okay, just know it takes a really long time to heat water up. Okay, that's why when you go to the beach and you take your little flippy flops off and you step on the sand and you're like, oh my gosh, okay, and you go down to the water and you're like, the water's cold. It's getting the same amount of sunshine as the sand, all right, but water stays cool longer and it holds in heat. Land, on the other hand, heats up really quickly and cools down really fast. So what you get this really cool effect with climate. If you are near water, you have a climate that has a smaller temperature range. All right, that's why I like places by like the beach. They don't get as cold as places that are inland. Okay, if you are inland, all right, you're gonna have a greater temperature range. So I'm thinking of a place like, Kansas. That's a good. Iowa. That's another good one. All right, the Great Plains. Nowhere near any big bodies of water. All right, during the winter time, it gets to like negative. It gets to the zeros, -5, -10, you know. You get those big blizzards. No, it's pretty cold in the winter. But in the summer, it's like 90 degrees, 95, 100, and you're like, wow, it's really hot. All right? But if I go to like, I don't know, the Outer Banks, all right, it still gets cold in the winter because we're tilted away from the sun. We're not getting as much sunlight. It's less concentrated. But it's going to be like 40 degrees, 50 degrees. And in the summertime, it's going to be like 80 degrees, 85 degrees, smaller range. All right? So Earth is heated up unequally. And we're going to get to more of that when we talk about weather and winds and climate and all that fun shenanigans. The other major importance of the sun, not only does it provide energy that heats us up and keeps us nice and roasted, toasty, warm, it provides us the greatest gift of all, which is food. Love it. All right. Plants, and if you're taking biology, you already know this, energy from the sun is absorbed by creatures called producers. Producers do a process called photosynthesis. Look at me going there. Photosynthesis. Photosynthesis basically takes light energy and turns it into food for either the plant or for some other organism. All right? We do not do photosynthesis. Okay? I cannot lay out in the sun and be like, a cheeseburger, please. No, I can't do that. But what I can do is I can go out to the garden and get like a carrot or a head of lettuce or whatever and be like, nom, 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 nom. All right? The energy I get from that plant started off as light energy, which was formed by this process of fusion in the sun 93 million miles away. So those are the two ways that the sun helps maintain life on Earth. All right, so I know this video was super duper long, but I hope it was helpful. Please let me know if you have any questions.